Howdy. Today for our project, our group will be presenting Michaelis-Menten kinetics for shear flow, which we solve using similarity solutions for a single step reaction, and furthermore it's generalized for a multi-step reactions. So we have 7 people in our group, the 6 of us, including Michael Scott, obviously. So for the introduction, biological processes consist of 3 components, that is diffusion, reaction and flow. However, most biological and microfluidic systems do not involve uniform flows but gradients in flow velocity, which actively stretch fluid elements and increase the area for diffusion and reactions. To express the importance of this system, here are some examples of these systems. The von Willebrand factor, which facilitates platelet aggregation for blood clotting, is stretched at high shear rates. Another example is when shear stress is exerted on red blood cells and endothelial cells due to flow in the circulatory system. They respond by releasing chemicals. These chemicals further modify the local microenvironment by diffusion and convection and induce biological reactions via enzymatic reactions. Drug release from patches also follow similar dynamics. These are important for us to understand as these dynamics are of great significance. For example, the flow in a developing embryo is believed to determine the left-right body axis of a vertebrate by triggering intercellular signaling via downstream transport processes. The enzymatic kinetics for the above examples are linked directly to shear flow as they conform to specific flow conditions, and the sites of chemical release or target are often fixed surfaces in the flow domain, with chemical reactions happening in the bulk. Now, despite these active interplays between diffusion, reaction and flow, most research till date focused on single step surface reactions with little to no work done to characterize nonlinear or multi-step reactions within the shear flow. Here we present a theoretical framework to characterize multi-step reactions occurring when an enzyme or enzymatic substrate is released from a flat solid surface into a linear shear flow. So here we discuss Michaelis-Menten kinetics, and enzymatic reactions are often nonlinear kinetics that involve interplay of 2 or more chemicals. In Michaelis-Menten kinetics, there's the binding of a substrate to an enzyme that produces an intermediate, when subsequently gives back the enzyme and produces a product, as we see in the reaction here. Furthermore, we restrict our attention to situations where fluid velocity, inlet concentration and boundary conditions are all invariant with time. The governing equation here is given as you see here. The left hand side shows us the convection term, which is equal to the diffusion term, and finally the reaction term. So here, as we see in this graph, this sketch shows us a linear shear flow where S denotes the substrate, E denotes the enzyme, and EI indicates the initial enzyme concentration flowing from the left, and SI the substrate concentration, initial substrate concentration at the right side where X is equal to 0. So under typical microfluidic conditions, the Peclet number is much greater than 1, and because of this the Peclet number is very large, and the standard boundary layer approximation applies, that is, the direction of the derivatives in the Laplacian are negligible compared to the y direction derivatives. Then in the case of a shear flow, here u is equal to mu y, where mu is shear rates, which has a unit of second inverse, and y is distance in the x direction. The steady state transport equation simplified for this specific case of Michaelis-Menten kinetics is shown here, which gives the 4 separate reactions. These equations are expanded on the equations for each reactant, intermediate and products as shown on the previous slide. Now the right hand side here contains the diffusive term, which complicates matters as the diffusion limits the rate of the overall chemical reaction. The latter diffusive effect is not considered, as here we assume well mixed conditions. Now we focus on the parallel laminar flow design, in which diffusion controls the volume where both substrate and enzyme are located. So here we have two classes of boundary conditions. One being the release of a substrate from a localized part of the surface into a stream containing the enzyme, and two, the enzyme released into a stream containing the substrate. Now in both cases, the extent to which the enzyme or substrate diffuses into the shear flow determines the effective reaction volume. Outside this region, the reaction rate is zero, as only one of the reactants is present. We resort to numerical methods for these above equations, as they are coupled and nonlinear. Now we get these equations to a dimensionless form that aids identification of the limiting cases where approximate analytical solutions are possible. The case of substrate diffusing into surface from surface into bulk where enzyme is present is taken care here. So here, for the dimensionless terms, the characteristic convective diffusive length scale that we take here is LD is equal to square root of ds by mu, and we get x, y, substrate, enzyme, intermediate and product as follows, where we have changed the equation for the substrate as the initial substrate concentration minus the substrate concentration divided by the substrate initial concentration. And we get the four equations in the dimensionless form, where the dimensionless parameters are as you see at the bottom of the screen: epsilon 1, epsilon of minus 1 and epsilon 2, where delta I is the diffusivity of the species that is normalized by the substrate diffusivity.
Alright, so I, Rhythm, would like to take over from here to present the similarity solution part of the project. Now, as mentioned by Errol in the previous slides, we would like to use similarity solution or simple affine stretching to solve the PDEs mentioned in the previous slide, as a system resembles semi-infinite domain setup. For that, we would make some sound approximations that would make us apply simple affine stretching. In the microfluidic system, the rate constant is generally from 10 to the power 1 to 10 to the power 7 molar inverse second inverse, and the shear rate falls anywhere between 10 to the power 4 to 10 to the power 5, and generally the substrate concentrations are higher. This leads to epsilon 1, which is the Damkohler number as mentioned here, to be very small, and that can be neglected from the main equation. We also assume that the forward reaction of the intermediate and product is faster because the intermediate is assumed to be short-lived. So we can neglect all the terms that are associated with intermediate concentrations. Now, after applying those approximations, we get the main equation as this, and this resembles Liebig similarity approximation. Solution. Now, applying simple affine stretching, we get the new S, X, and Y as this, and by plugging these S, X, and Y in the main differential equation above, we get this, and simplifying it further, we get this. Now we look for the condition which are invariant to stretching and get the values for B upon C cube and C, which can be again written as C over B to the power 1 by 3 for to make sure that all the complexities goes to the independent variable, which is which has least complexity, and we get A equals to 1 from the boundary conditions. We also couple the independent we also couple the parameters in the way like this, where eta is equals to y over x to the power 1 by 3, and for the simplicity of solving the equations, we get eta as y over 3x to the power 1 by 3. Now, for the boundary conditions, we have made slight changes in the dimensionless substrate concentration. We assumed here that S, which is the dimensionless substrate concentration, is equals to Si minus S over Si, following only which we were able to get the results mentioned in the paper. This has been described in the later slides and in the report as well. So according to the boundary conditions, we get as at x equals to 0, Si is equals to 0 as there is no substrate in the fluid, which implies this S is equals to 0. S is equals to 1. My bad. At y equals to 0, there is a substrate layer which is at the boundary, and therefore the concentration of substrate is Si, which implies that S equals to 0 at eta equals to 0. And at region farther away from the substrate boundary, that is eta equals to infinity, which is y equals to infinity, the diffusion of the substrate is not significant, and that can be assumed to be 0, which implies that S is 1. Now, applying these boundary conditions and coupling those parameters x and y, we get an ODE in terms of f and eta. And by applying the boundary conditions, we get the differential. We are solving the differential equation, and we get the substrate concentration as a ratio of incomplete gamma functions. Now, if you have noticed, by employing those approximations, we neglected the reaction terms in the original differential equation. That means the substrate concentration in the above solution should be maximum. In the presence of reaction, the concentration should be less. For other components in the fluid with no reaction conditions, the concentration of enzyme becomes this, for which the enzyme concentration is considered to be in excess for microfluidic systems. Now we have all the concentration of the components without reaction, and now we can establish a perturbation solution. Following that, we get the equations for the intermediate and product concentrations to be this and this. And we also substitute the similarity variables, and following that we get the concentrations of the intermediate and product to be assumed as this and this. Using above equations, we develop the system of ODEs as follows, and for which the boundary conditions are such that there is no flux of the product and intermediate into the solid surface, and the concentration far from the surface is 0.
Thanks, Rhythm, for explaining us the similarity solutions and the boundary conditions. Next, we'll be moving on to the Maple algorithm and solutions. These are our results that we extracted from Maple, showing us the similarity solutions for both equal and unequal diffusivities with respect to eta. Here we have our Maple algorithm. Firstly, we add all the modules that will be needed. We add array tools for plotting our vector solutions, which we'll cover in the later section. Equation 1 to 3 are ODEs, which we were defined earlier. We take those ODEs and solve them numerically to get our solutions. Equation 1 describes the change in concentration of substrate with respect to eta. Here, psi represents substrate concentration. Equation 2 describes the change in concentration of intermediate with respect to eta. Phi describes intermediate concentration. Similarly, equation 3 describes the change in concentration of product with respect to eta. Alpha over here describes product concentration. In equation 4 and 5, we substitute the values of delta ES and delta P in both equation 2 and 3 respectively. Now we define our boundary conditions for phi in equation ICEQ4, alpha in ICEQ5, and psi in ICEQ1. Now we merge all the equations into one equation. We feed the equations and all the boundary conditions to D-solve function. We are looking for a numerical solution. Our mesh size and absolute error values are defined to get highly accurate numerical solution. We obtain the output in form of a procedure. Once we have our output, we extract the values of alpha, phi, and psi with respect to eta and plot it. Over here, we can see the plot of concentration change for all alpha, phi, and psi with respect to eta. As we can see from the plot, the green curve represents the change of substrate concentration, blue curve represents the change of intermediate concentration, and similarly the red curve represents the change of product concentration. As we can see, the substrate concentration starts close to 1, whereas the intermediate starts around 0.4 and the product starts around 0.12. All the concentrations converge to a value of 0 at eta value of 2. Once we have the plot for equal diffusivities, now we move on to the change of diffusivities by changing the delta values of both intermediate and product. Equation 7 substitutes delta ES as 0.1 in original equation 2. Similarly, equation 8 substitutes delta P as 1 in our original equation 3. Again, we merge all of our equations and solve them using the dsolve command. Once we solve the equations, we extract the solutions and plot them using the plot function. And as we can see from the plot, the intermediate concentration starts at a higher value because of the change in diffusivity. This means there will be more intermediate at the surface compared to the bulk. We also observe that the intermediate concentration falls below the product concentration near eta value of 1, as described in the original paper. We also made a preliminary contour plot for substrate concentration to understand the profile under laminar flow. From the plot, we infer that we will occur a waning concentration profile of substrate in the y direction. We will look at it further in our COMSOL simulation. On to our COMSOL file. These are our results for the COMSOL simulation for the contour plots for substrate, intermediate, and product. We'll look into them further in our COMSOL file. So here we have our COMSOL simulation file open. We will show you a brief description of how we can set up a new COMSOL module. So let's start with it. The first thing we'll do is click on Model Wizard. This will give us an option to select any kind of space dimension. For our problem, we'll be using the 2D space dimension. We'll be selecting chemical species transport for our problem, in which we'll be selecting transport of diluted species. Once we have added the transport of diluted species module, we're going to select laminar flow for our case. Once all the physics modules are added, we click Study. And since our case is going to be stationary, we won't be selecting the time-dependent module. Finally, we have our COMSOL simulation set up. So the first thing we did was we defined rectangle as our geometry with x ranging from -1 to 5 and y ranging from 0 to 3. The dimensions were chosen to replicate the figures in the paper. We added a vertical line segment at x equal to 0 to assign our boundary value conditions to the problem. Next, we go on to our materials. We choose water as our transport medium for the simplicity of our problem. Now that we have defined a material, we move on to the transport of diluted species. The first thing we look into is the transport properties. The diffusivities chosen for this case were based on standard diffusivities for common fluids. Next, we have our no flux condition across the boundary as shown by the blue segment. For our inflow conditions, we define that the fluid will be flowing at x equals 0 as represented by the blue lines. For our outflow, we define that the fluid flowing out at x equals phi. Now we define our concentrations. The substrate concentration at y equals 0. Since substrate is present only at the surface, we define the substrate concentration as 1 on our surface based on dimensionless variables considered during our previous derivation. Then we define all the concentration as 0 at the upper boundary, which is at y equals 3. Finally, we define our surface reactions. First, we define intermediate formation reaction with rate coefficient equals 1. For substrate, the reaction rate considered was -1 times C1, and intermediate formation rate considered was 1 times C1, which is substrate concentration. And the product formation rate. The product formation rate was considered very low to encompass that not all intermediate converted to the product on the surface. This was also done to prevent fast irreversible reactions, which would not give us a concentration profile for the intermediate, as all of it would immediately convert to the product. Once we compute all of this, we get our resultant plots. This is the contour plot for substrate. As seen, it shows a waning profile in the y direction as predicted by our Maple code. This is the contour plot of our intermediate. As seen, it has lesser diffusion in the y direction compared to the substrate. This is due to delta S ES value chosen as 0.1. Finally, this is our contour plot for the product. As it can be seen, these profiles intuitively describe the reaction rates of the system. Primarily, as we see that the substrate is in abundance, it starts diffusing into the flowing medium right away. As the fluid flows through the channel, the reaction occurs and the intermediate is formed. After some time, the intermediate formed starts diffusing into the flowing medium. The difference in the points at which the substrate and the intermediate just start diffusing into the medium can be considered as time representation of the reaction rates. Similarly, we see that the product diffusing a little further in the x direction after the intermediate starts diffusing.
To get an idea of concentration of the components in the system, we are calculating average concentration of intermediate and the product, which can be evaluated by using these expressions. And in the dimensionless terms, it can be written as this, where A delta and B delta are dimensionless constants, which are described as this. These constants have weak dependency on diffusivity species, which can be represented by the plot A delta versus delta S and B delta versus delta P, which Shanice is going to present.
Thanks, Rhythm, for explaining us the definitions of A delta and B delta. Next, we'll look into our Maple algorithm to see how these constants vary with the change in delta ES and delta P. This is our result of the Maple simulation. Let's look into our Maple algorithm. So now let's see the Maple code for both A delta and B delta constants. Since A delta and B delta are a complete integration of psi and phi respectively, it means that we will have to solve the coupled similarity ODEs at different values of delta ES and delta P. For A delta, we vary delta ES, and for B delta, we vary delta P at different values of delta ES. First, we define NR, which stores the values of area under the curve. We define B del average to capture different values of B delta. Since the plot is semi-log scale, we define a vector U which contains values in semi-log space. It uses vector V as a basis, which basically contains values from 1 to 9. We multiply each V value with different powers of 10 to get the semi-log space. The next segment consists of two nested loops. The outer loop is used to define the similarity variable ODEs at different delta P values, and obtain the numerical solution of coupled ODEs via dsolve command. Then we extract the alpha values from the solution procedure and move on to the inner loop. In the inner loop, we carry out the integration of gamma, which is denoted by alpha year, over the entire range of eta. We choose a step size of 0.01, hence the number of iterations are 10,000. We use the trapezoidal rule of integration to calculate the area under the curve at every time step. Once we obtain these values, then the summation of these values gives us the entire area under the curve. We obtain B-del average by multiplying the area by our coefficient mentioned previously in our equation. These are the U values we obtain for our semi-log space, and these are the values of B-del average. Using the same algorithm for different delta ES values, we get a resultant B deltas. Over here, for our B del average, the delta ES value used is 0.1. In this case, we use delta ES value as 0.01, and initially we had used a delta ES value of 1. Similarly, we calculate A delta values for varying delta ES. We use similar algorithm as above. The key changes here are we vary delta ES value instead of delta P. We obtain values of phi from ODE solution and integrate it to get A delta values. Finally, we plot both A delta and B delta values and we change the x-axis to a log scale. Over here, you can see our plot. If you right-click on the plot, you can change the axis to a log scale. As seen in the graph, this is an exact replica as depicted in the paper.
So you have seen the reactions of if there are just one step and there's just one intermediate. But now let's build some blocks and generalize it for the n reactions. Now you see a reaction of suppose which is of this form here, where there are n steps and there are n minus 1 intermediates here. Now we will try to bring form equations for these reactions as well. Here again we do not consider any back reactions, and we have neglected the diffusion in x direction due to the large Peclet number, and consider the reaction in diffusion to be invariant of time. All the reactions are first order except for the first reaction, and here the enzyme is again assumed to be in large excess when the substrate is again starts diffusing from the surface. When all these criterions are met, we can again form this perturbation solution for the intermediate and the product here. Now suppose we can see for the intermediate of suppose the jth step here depends upon epsilon 1 up till epsilon j, because there are j steps here, and it depends upon x power 2 power 2 j by 3 here. And similarly for the product, since there are n steps here, it depends up till epsilon n, and it depends upon x power 2 n by 3, as you have seen similarly for the first just for the one step reaction. So now if we substitute these equations in the ODs which you have seen, you get the ODs here as you can see here in terms of phi dash and gamma dash here, similarly as you have seen for the single step reaction. And similarly, as we draw similar analogy, the integrated product concentration again is quite similar to what you have seen for one step reaction. It depends upon all the rate constants from K1 up till Kn. It depends upon the initial substrate concentration, the enzyme concentration, the diffusion, and also the imposed shear flow. It is quite important. And finally, the most important factor is how much distance it has traveled. So as we come towards the end of this presentation, we would also like to put some concluding remarks here. In a single step reaction, we have seen that the average concentration increases with distance with x to the power of 5 by 3. This comes with the assumptions that the reaction is really slow and the shear rate is very high. Also, a similar methodology has been employed for co-flow microfluidic networks where the reactants which come from the surface where the substrates are released are brought together in two converging channels. But the present results provide a method for assessing situations where a reactant is released from a solid surface. We have also seen that the product concentration in the before slide is quite dependent upon the shear rate to the power of 2n plus 3 by 3 here. As you have seen here, it depends upon gamma as 2n plus 1 by 3 here. So it is highly sensitive to the imposed shear rate. Also, when it is inconvenient to probe multiple positions along a micro channel, an alternative approach would be to measure the product concentration at a fixed location while varying the imposed flow rate. Now, we at times there might be situation where we will determine the product concentration with the position. Suppose we do not know the how many steps are there, but we can know the number of steps from these equations, which is like as an example for a 3-step reaction, the product concentration increases as x power 7 by 3, while for a 4-step reaction it increases as with x cube. So basically this is quite awesome because as we know the product concentration how it varies with x, we also know automatically how many steps and how many intermediates are there by just measuring the product concentration versus the positions. So in our future work we would also like to discuss some drawbacks in this work as well. In this present work, we have considered that there are really slow kinetics with negligible back reactions. So we need to also see how the calculations would vary when there are faster kinetics and when the significantly back reactions are also predominant, which means that both the reversible reactions come into play here. Likewise, we have seen that the similarity solutions which we have assumed here assumes linear flow, which means that as we move away from the surface, the effect of no slip condition varies. The no slip condition mitigates as we move towards the center, and this varies linearly with the position. But there are situations where it varies parabolically, so we need to consider that also. So also we need to see more detailed calculations if the effective reaction zone extends past the region of linear shear near the solid surface, or if the substrate is released within the entrance region of a micro channel where the linear shear profile is not fully developed. Also, in many biological interests, the amount of reactant released actually depends upon the imposed shear rate. Hence, shear rate plays an important role, as we have seen how the product concentration depends upon the imposed shear flow. So, as we conclude, we also see this solution will provide us as the base case for considering more complicated efforts. Well, thank you for going through our presentation from the start to the end. At most, we would like to thank Dr. Gagnon for giving us this project and for doing this COMSOL project, and help us in giving us such cool graphs here, because now we are able to draw analogies from how we were able to derive it on paper to seeing the solutions on COMSOL. So that was a really cool project for us, and thank you all again.